With the development of this numerical method, when we look at the status of computational electromagnetics, one can see that computational electromagnetics is relatively mature area. For most pure electromagnetics problem, we not only know how to solve these problems numerically, but we also know how to solve this efficiently and accurately. So in recent years, the electromagnetics community has been thinking about the future direction of computational electromagnetics. And like one of the challenges for future research is multiphysics challenge. Now, in reality, for many practical engineering applications, the electromagnetics phenomena do not exist alone. It's always coupled with other physical phenomena. So, for example, in many cases, electromagnetic processes are coupled to thermal phenomena. And for electronic devices, high power microwave devices, and accelerators, equations of electromagnetic field are also coupled to equations of electric particles. So handling electromagnetic interaction with an electric particle is also an existing and challenging problem. So for electromagnetics, it's also coupled to mechanical problems such as pressure, as well as acoustic problems with vibrations. So if we go down to nanoscale, and electromagnetics can be coupled with quantum physics and nanoscale devices. So differential equation solvers are used for almost exclusively in many fields because of nonlinearity of relevant equations. And on the other hand, because of the linearity of Maxwell equation, analytical techniques such as involve time domain approach and the integral equation can be used to arrive at alternative methods to solve electromagnetic equations. And we can also use integral equation solvers. Traditional integral equations are efficient, but with the development of fast solvers, they're more efficient than before and become even more efficient than differential equation solvers in many applications. It has been interested in applying differential equation techniques to solve electromagnetic equation, and when applied to aircraft scattering problems, these solvers use resources that scales more efficiently in comparison to fast integral equation solvers. So one way to reduce the scaling law in resources usage is to combine differential equation solvers with integral equation solvers, where the computational domain is truncated by the fast integral equation solver. So if memory and CPU resources are not an issue, then differential equation technique can be used to obtain broadband simulation data for electromagnetics. And if memory alone is not an issue, then fast time domain integral equation solver can be used to obtain broadband data electromagnetics. And one complex problem that calls for more sophisticated computational algorithm is the simulation of complex structure inside a computer at the level of the motherboard and package and chip. And it involves multi-scale features that cannot be easily tackled using conventional methods. So many electromagnetics problem involves complex structure where one of the parts is a sub-wavelength size, and at the same time another part is characteristic dimensions of multiple wavelengths. When these two types structure coexist and have to be modeled with a single numerical method, we have to overcome additional computational challenge. In this case, we can have discretization on one part of electromagnetic problem, which is several orders of magnitude smaller than the other part, and it becomes a very big challenge to get a solution efficiently and accurately performing numerical calculation of this kind of numerical discretization. So here I list some problems ranging from low frequency regime to high frequency regime, and I would like to give you some examples. So in US Army typically consider a four-step process in modeling antenna on platform problems. And then the first step involves the development and validating electromagnetic model for each antenna. It's considered to be part of the integrated system. And then part of the process require detailed modeling of antenna physical structure, feed design, excitation, and rhythm. And antenna metric is typically measured and modeled as a far-field radiation pattern. So this preliminary antenna model is then simulated in free space using an appropriate numerical method and obtain radiation pattern. In parallel, to obtain practical radiation pattern, antenna is measured in free space in room with the correct dimension designed to absorb reflection completely. And once the two data sets are obtained, the predicted results are compared with the free space measurements of the antenna. So the second step involves validating the military platform and any rooftop abstraction under consideration such as gun protection kit, weapon system, and this step typically involves a complete survey of the vehicle to capture platform configuration detailed for accurate platform modeling. And the third step is to construct complete numerical electromagnetic model. It includes antenna, platform, and other additional object with the electromagnetic properties. And the fourth is, in the final step, is to compute the radiation characteristic of each antenna for the non-antenna on platform configuration. And the calculated antenna radiation patterns present the realistic 3D antenna pattern.